We will have a welcome note by our current ISRE president, Mr. Karthikeyan Ganeshan.
Thank you, Shailesh. Good evening, everyone. Hope everybody is doing good. Myself, Karthikeyan Ganeshan, the current chapter president of Qatar History. Once again, I'm welcoming everyone. So, hope most of the people well aware of history. So, it's my duty to just start the presentation about a few minutes, talk about what is history, so how it's benefited to the people in our industry. So, thank you for the opportunity. So, I'll be sharing my screen. Hope screen already shared visible, Basha.
Yeah, it's visible.
Perfect.
Good evening, fellow Israelites. I'm extremely sorry that I.
So basically, the history, as you guys knows, we are in the third year in Qatar. So after successful complete for the 2 years, we are in the third year running successfully in Qatar. So we have close to 300 members in Qatar. And overall, if you see 25,000 plus members we have, and more than 61 chapters and sub-chapters around the world. So we have our community was grown into the international chapter, currently 6 international chapter with Qatar, Bahrain, Dubai, Nepal, Nigeria. So in another 3 more chapter was on the way to launch. So we have multiple activities, and we have biggest events are coming up. So as soon as the members will be giving the complete details about the events yearly and monthly, what kind of events we are doing. We have technical seminars, workshops, conference, and technical talks, product presentation, panel discussion. And apart from that, we have social and non-technical events, and every year we are conducting within our members and to our community. So there is a huge range of resources available, and we have a history certified engineering professional ICP. We can share you the complete information and very soon. And we have membership details and publications. Membership detail will be on the moment that we joined in the group and WhatsApp group for the seminar. So we will be sharing all the information. What is the benefit of members once you become the members in Israel? So we have a lot of technical things. We are upcoming Across is coming. So this is a quick introduction for the history. So the seminar, mainly the webinar was planned for a technical event. So I don't want to take more time on the introduction on this. So I'll be leaving to Mr. Shailesh. So he'll be continuing the seminar. Thank you once again.
Thank you, Karthikeyan sir, for the welcome note. This webinar is a platform for all of us to learn, share, and grow together, to explore the latest advancements in the HVAC technology, tackle the unique challenges of working in Qatar's climate, and exchange ideas that can elevate our industry and our career. Today, we are honored to have Mr. Mohammed Basha with us. Before we go any further, I would just like to give a brief introduction about Engineer Basha. He's an experienced mechanical engineer with over 17 years of expertise in building services. He is an incorporated mechanical infrastructure, fire and life safety engineer, licensed by the Engineering Council UK, and he also holds a PMP certification. His experience includes design, execution, site supervision, and quality control in plumbing, drainage, fire protection, suppression, and HVAC systems. He also holds NFPA from USA for a certified fire protection specialist and hazard recognition specialist. Currently, Mr. Basha is pursuing to be a chartered engineer through the Institute of Fire Engineers UK. In his past role as a senior engineer, senior mechanical engineer working in KEO International Qatar, he has demonstrated a very strong understanding of relevant British and American international standards, and he also possesses a very extensive knowledge of NFPA and civil defense requirements. I would encourage each of you to participate actively, ask questions, and make the most of this opportunity. On behalf of Ishresh CWC committee, I extend a very warm welcome to all the participants, whether you are joining from your office, from your home, or even at site. Together, let's make this session a very insightful, engaging, and above all, inspiring session for all of us. Mr. Basha, over to you now, sir.
Hi. Thank you, Mr. Shailesh, and thank you, Mr. Karthikeyan, for giving me this wonderful opportunity to hold this webinar. And thanks for all ISHRAE members who took the time and efforts to attend this webinar. We make sure that it fulfills your requirements. Can we start?
You can share your screen.
You can start, Mr. Basha. You can share your screen.
It's visible, sir. Your screen
It's
is
visible.
Yes.
Okay.
If you can just put it in a presentation mode so that it's easier for us. Yeah, perfect, sir.
Okay. Welcoming you all for the technical webinar on smoke control system design and applications. The main concept of having this smoke control system to the HVAC engineers who is member of ISHRAE is the thing that the equipments for the smoke control system is being selected often by mechanical engineers. It's not the fire and life safety engineers. The equipments in the sense I'm referring to the fans, the location of the fans, the number of the fans, the capacity of the fans. So we would like to go into more technical in detail to know the principles, to know the basics and understandings of the systems. I want to put a disclaimer here. The view, analysis, opinions expressed in this presentation are solely those of the presenter, which is me, and it does not reflect any official policy of my company or the AHJ or the software which I'm going to use. This is purely for educational and informational purpose. And it is not to be taken as official guidance or endorsement by any organization or any personals. Okay, the learning objectives. What are we going to see today? By end of the sessions, you all will be able to understand the different types of smoke control systems for atriums and car parks as referenced in NFPA 92 and Qatar Civil Defense requirements. Basically, Qatar Civil Defense requirements is moreover equal to NFPA 92, but they have some additional requirements in terms of car parks, which is BS 7346. And understand the terminologies referenced in NFPA 92. Differentiate between sprinkler controlled fire and fuel controlled fire. Describe the concept of heat release rate and its impact on smoke production. Identifying the sprinkler activation timing and its impact on heat release rate using Allpurpose correlation equation. And how the sprinkler timing activation influences the heat release rate and subsequent smoke production. And analyzing the effects of jet fans operated during the fire mode. So this all objectives will lead to a final point that how to design a proper smoke exhaust system. And to do this, we need to select the proper equipments, which is the fans, the capacities, the number of outlets. So let's look into the smoke control system basics first, because we often used to hear smoke control system. But what exactly is smoke control system? How many systems are there? Smoke control systems are divided into two types, as you can see here, which is smoke containment system and smoke management system. So smoke containment system, it works through the pressure difference between the barriers. Means you are containing the smoke in one place by creating a pressure difference between one space to another space. The examples are stairway pressurization, elevator pressurization, zone smoke control, refuge area pressurization, and vestibule pressurization. The next item is smoke management system, which is completely different working concept from the smoke containment system, which is natural smoke ventilation or mechanical smoke exhaust system. This is working through extracting the smoke from the area by natural or mechanical means to maintain the tenability. What is tenability? Tenability, it refers to the condition where it is suitable for the occupant, for the occupant evacuation, or for the occupants to be there in that space. That is called tenable condition, we say. So the main purpose of smoke management system is to create a tenable condition for the occupants to leave the area affected by fire. Whereas the smoke containment system prevents the smoke from entering one area to other area by pressurizing the non-affected zones, whereas smoke management system extracts the smoke, and the smoke will be there in that enclosure, but in a higher level. So this is the fundamentals in smoke control system. What is smoke containment and what is smoke management system? Because we use a single word called smoke control system. It has a different names and different systems to be used. In smoke management system, we have another system is called smoke clearance system, which I have not referred here. Smoke clearance system, it is called as smoke purging system as well. It is used for after fire event to remove the byproducts of fire, which is the carbon monoxide or smoke exhaust, after the fire is being extinguished. So the objectives of our course, which was outlined in the group or anywhere, it is mentioned as atriums. So what is the smoke management system required for atriums as well as car parks? So first we are focusing on atriums. So what is referred as an atrium? Because you have to define it properly, whether the space is atrium or it's a communicating space or it's a vertical opening. So we need to understand exactly what is called as atrium, because atrium only requires smoke management system. The other openings, for example, you have escalator openings, right? You can see in the malls there is escalator openings between the floors. This is not called as atriums. This is called as convenient openings. And you can see the shafts or the staircases inside the building, which also opens from one floor to another floor, but which is called as vertical openings. So the atrium is the area where you need to have a smoke management system. Why it is? Because atrium is open to the vertical open space is open to the communicating spaces next to each other. As you can see in the figure, left or right, the right side is more familiar to us because it's from the HIA, Hamad International Airport. The left side is taken from the internet, just to show you an example. As you can see here, you have big open area and you have multiple levels which is communicating to the atrium, which means open to atrium. If any fire happens in the atrium, it will be passing to the communicating spaces as well. So we should ensure that the smoke generated by the fire will be taken up directly without allowing the smoke to pass inside, to maintain the tenable condition for the occupants to go outside. This is the purpose of the atrium smoke management system. So what is the definition of atrium as per NFPA 101 or any other standard? This is the common definition. A large volume space created by a floor opening or series of openings connecting two or more stories. This is the definition. Two or more stories that is covered at the top of the series of opening and is used for the purpose other than an enclosed stairway, hoistway or escalator opening, or a utility shaft for plumbing, electrical and air conditioning or communicating facilities. As I mentioned before, the openings are classified into different ways: communicating spaces, convenient openings, vertical openings, atriums. So the focus here is an atrium, because which is the place where we need the smoke management system, because it is open to the smoke generated space and we need to maintain the tenable condition for the occupant to go away. For example, if the atrium space, you have this building, but it is all covered by glasses, then this building is no more referred as an atrium. You do not need to have a smoke management system. Since the space is open to since this communicating space, that is the corridor, is open to the atrium, then we need to have a smoke control system. For example, you might have seen in some buildings, they will be having a fire curtain here. In case of fire, the fire curtains will be dropped down. which will separate this area, the communicating space to the open area. In this case, you do not need to have a smoke control system because occupants can evacuate from this space, but still it's local authority having jurisdiction who will decide whether do we need to have a smoke management system or not. For example, in Qatar Civil Defense, if the area is bigger than 1,115 square meter, they were requesting to have a smoke management system. Okay, what are the types of smoke control system defined in NFPA 92? There are 5 types mentioned. I have shown you 3 types here because the other two types are not commonly used, but I will explain you about that. The first type is natural smoke filling. Natural smoke filling is not a commonly used smoke extraction method. It's not a smoke extraction method. It's a smoke filling method. Basically, we allow the smoke to build up at the high level. Then we will see how far the smoke needs to how long, you can say in time seconds, how long that the smoke needs to come down to a occupant tenable height. If the time required for the smoke to come down till the occupant height, we need to see the time, and the time for occupant evacuation also needs to be considered. If the time for occupant evacuation is lesser than the smoke filling time, then you do not need to have a dedicated smoke control system in a building. This is called natural smoke filling. Basically, we are filling the smoke as a reservoir at the top of the building. This will not be applicable in the atrium because you will have a communicating spaces in the atrium. We cannot allow the smoke to fill up to the bottom, which is not commonly used, but it can be used by accepting the proper fundamentals. And Qatar Civil Defense is not recognizing this method, but other jurisdictions, they are recognizing. For example, I'm in Riyadh here. Here, we do not have such stringent requirements. If you comply with International Building Code or International Code Council requirements, you can use this. Mechanical smoke exhaust. This is the common system we will be using, which will be having the extract fans at the high level to extract the smoke out of the space. To maintain the interface height. It must be calculated based on the smoke layer height you need to maintain at a predefined height and designed for a specific time duration. Mechanical smoke exhaust delay descent. This is also not commonly used. In this case, for example, the previous case I mentioned, maintain interface height. There, if you are using X capacity of fan, in the second line, mechanical smoke exhaust, we will not be using X capacity, we will be using 0.5 X capacity. So we will allow the smoke to get down by the time passes, so the occupant can evacuate. The next method is opposed airflow method. This is one of an important method, but again, it is not commonly used. It is operated by using high velocity airflow to block the smoke spread between the connecting spaces. I will show you in a figure in the next slides, so you will understand. So this is called a natural filling of smoke, no exhaust. So you can see the top space, it is called a smoke reservoir because when a fire develops, the smoke goes vertically up and it hits the ceiling, then moves radially, then it starts to descending down. In this case, the space between the soffit, which is the top of the slab and top of the occupant, is very less. It is not desirable to use such kind of a system in an atrium. This is what I was explaining in the previous slide. If you don't have this atrium spaces, like the communicating spaces here, then you could use this system to get the time needed for the smoke to descend down to this level. So example, if you need 180 seconds for the smokes to come down to up this level, and you need to see the occupant evacuation time at this level, how long they need to evacuate from this space. If this speed, the evacuation time is lesser than the smoke filling time, then you could use the system, but it must be analyzed well with the CFD analysis. So is this method acceptable to QCDD? No, it is not acceptable. For other jurisdictions, yes. This methodology is mechanical smoke exhaust. As you can see, common everywhere. You will have a smoke exhaust fans in the top or in the side, which we will constantly taking the smoke out of the protected area to maintain the smoke interface layer. We call this as the free area, and this called a smoke interface layer. Smoke interface layer means the layer that separates the hot gas and the cold gas. The layer below the smoke interface layer is called as tenable environment. So mechanical smoke exhaust is smoke exhaust fans, controls, dampers, of course, fire alarm system, damper operations, of course, fresh air fans. Is this method acceptable to QCDD? Yes. Other jurisdictions? Yes. Opposed airflow. This is certainly new for our region. No one will be using this, but it is also a good methodology to use. The main purpose of opposed airflow system, opposed airflow type of smoke control is it is not intended to remove the smoke from this protected space. It is intended to avoid the smoke penetration from this area, which is the large volume area, to the communicating space. How it works, you will have a fresh air fan here, and you will be pushing the air with a certain velocity to keep the area smoke free. It is basically a kind of smoke containment methodology, but it does not create a pressure. So that's why it did not come into smoke containment system. It is still a smoke control system, because here there is no need of maintaining the different pressures, which is the pressure differential delta P we used to measure in the staircases. Here we are just flowing the air with a certain velocity to keep the smoke coming out of the communicating space. This is called opposed airflow method. There are three types. As you can see, you can push the air from the top area, and you can push the air from this area. This area is this kind of system is a more critical system, because there's a caution here. Assuming a fire happening in a communicating space, fire is not happening in the atrium, whereas in this figure the fire is happening in the atrium, but here the fire is happening in the communicating space. So we do not want the smoke to come out of the communicating space to the atrium space. So we will be introducing the fresh air into the fire area. You know very well the fire triangle. If you are introducing oxygen more to the fire, the growth of the fire will be more, and even the sprinklers cannot control the fire at certain cases. And another methodology is again throwing the air from the communicating space to the smoke layer. So the difference between this and this, you can see the fire location. In this one, the fire is located at the corner. Basically, here only one communicating space is there. So we do not want the smoke to go out from this space. Whereas in this condition, the fire is located somewhat far away from the communicating space, and all the spaces are open to each other. Why they are pressurized? Why they are forcing the air only from the top? Why it is not at the bottom? The reason is, during the fire scenario, when the smoke is produced, the first smoke layer will be developed at a 20% of the ceiling height. If you have a 3-meter ceiling, the first smoke layer developed will be 0.6 meters. That is the first layer of smoke will be developed. And if you have a 20-meter high ceiling, again 6 meters is the first smoke layer development. Then only the smoke starts to descend down. So when it is starting, when the smoke is starting, when it's coming down, I do not want the smoke to go inside in this space at the first. So I'm pushing the smoke out so that the occupants in this space can come out. When the occupant can come out from this space, and occupants will be alerted at this place to come out. So this needs a sound performance-based engineering calculations to have this kind of system, rather than having the mechanical smoke extract system. The concept why we are explaining is to help you understand the types of smoke control system available for an atrium, because atrium smoke control is not a common we are seeing in all places. It will be used only in a specific kind of a buildings, like when you have a shopping malls, or what else, when you have a big conference centers or airports. Okay, some basic terminologies we need to understand before we jump into the next slides, because the next slides are going to be more technical rather than a theoretical approach. So we need to understand some terminologies. Now, if you look into this figure, it shows a fire develops and hot gases going up. The fire develops and the hot gases rising up at a center without any interferencing is called as axisymmetric fire. If it is fire happening at the corner, we will call as corner fire. the plume development, plume means the diameter of the fire basically, will not be the same as what is happening at the fire in the middle or fire in the sides. This type of fire growing without any obstruction to the walls, which will be round in nature at the beginning, which is called as axis symmetric plume. So if you see the characteristics, the D is the diameter of the plume. It can be hot gases also at the initial stage. The dynamics, if you look into this fire, when a fire starts, the smoke develops. It doesn't go in this way as shown in the figure. It goes first, it hits the ceiling. Okay, then it starts going down. It will turn down. It will turn down and come back. The turning down is called as turning region. So initially the smoke goes vertically up, hits the ceiling and turn down and go like this. So this is called turning region, and this is the first space filled with the smoke. So H is the total height of the building. You can say the floor or story. Z is the clear height below the smoke. Z1 is called limiting elevation. You can see here H, Z and Z1. Z is called what? The clear height below the smoke layer. This is called a tenable environment, the Z. Z1 is called limiting elevation, which we will not consider much, but I will explain you what is that. Limiting elevation is the lowest acceptable height above the floor to which the smoke layer interface. But Z1 will be sometimes higher. But if you can maintain the Z, which is the clear interface height, you will be complying to Z1 as well. And there are certain fundamentals also to understand. We call in the smoke management calculations or in the fire calculation a alphabet called Q. Normally for HVAC engineers, Q is GPM, or PHE, plumbing engineers, it's called flow rate. Here, Q means it's the heat release rate of the fire. Heat release rate, I will explain you in the next slides, which is the output of the fire, you can say. QC, which is called convective heat release rate. Fire is developing, okay, this much amount of heat it is releasing and it much amount of temperature it produces. But what happens to the next to the fire? You will be having some convective heat transfer. So how much the convective heat transfer, which is the 70% of the Q. So QC is called as convective portion of heat release rate, which will be 70% of the Q. Z, I explained to you, distance from base of fire to smoke layer. Z1 limiting elevation. M is exhaust mass flow. R is the gas constant. T is smoke temperature layer. TO, ambient or outdoor temperature. Then the next are constants. Smoke density, atmospheric pressure, volumetric flow of smoke exhaust, convective fractions. We will discuss more when we go into the next slides. Before we understand the Q, the fire, we need to understand what are the types of fire we have. What are the types of fire we will be taking into consideration in the design. It is not only for smoke management system, it is for all kind of fire engineering design. There are two types of fire based on its growth we distinguish. One is called T-squared fire, another is called steady state fire. Let us see steady state fire. What is it first? A fire that maintains a constant release rate after reaching its peak. This is like a burner, okay? You like a candle, you can say. You start a fire and the candle will continue to release the same amount of heat until the candle loses its mass, right? There is no differences will be in the heat release rate. The amount of energy it producing. It will be like 10 kilowatt at the beginning. At the end of the candle also, you will have the same 10 kilowatt. This is called steady state fire. T-square fire. This is the actual fire what we will take into consideration for calculation purpose or for analysis purpose. T-square fire means a fire that grows rapidly with HRR, I call as HRR for heat release rate, increasing as the square of time, or where the heat release rate increases proportionally to the square of time. Let us take the second definition. T-square fire means where the HRR increases proportionally to the square of the time, representing how real fires grows rapidly from ignition. You know, when you have a car or when you have a sofa, when the sofa is burning, initially it will burn at one place, releasing 1 kilowatt of heat energy, let's assume. Then the fire starts to move further because of the next combustible materials, and it's burning and burning and burning. So at every time seconds, the heat release rate will be varying, increasing. It's not decreasing or the same, it's varying. So when the heat release rate varies based on the time, then it is called as T-squared fire. And the T-squared fires are further classified into 4 types: slow growth fire, medium growth fire, fast growth, and ultra fast growth. You might be wondering, why are we discussing this? It is not irrelevant to HVAC engineers, but it is relevant for the smoke management system, and it will ultimately help you to decide the capacity of your smoke extract fans, and which in turn decides how much outlets you need to have. As you can see in the curve here, which is the left side, which we call them as HRR versus time curve, you can see the different colors: cyan color, red color, and green and magenta. You can see this represents slow growing fires. Slow growing fires will reach 1000 kilowatt. This is called as kilowatt, which is 1000 here basically. It will reach 1000 kilowatt at 600 seconds in a slow growing fires. Medium growing fires, it will reach at 300 seconds, 1000 kilowatt. Fast growth fire will reach within 150 seconds, and ultra fast within 75 seconds. So you can see the examples. What are the fires? Slow means densely packed wooden products, art gallery. Medium, solid wooden furniture items, office. Fast, shopping centers, library, theater. Ultra fast, upholstered furnitures, which is the I mean, you can see the upholstered means the types of furniture in the car, which is upholstered, or sofa is upholstered. High stack plastic materials, thin wood furnitures, chemical plants, storage buildings with alcoholic liquids. So this is called ultra fast fire. For the purpose of design and calculation, T-square fire will be used because it shows the actual growth of the fire, where a steady state will not grow the actual condition of the fire for us to design. There are 2 types of fire also, we can say 3 types of fire basically, but 2 types are majorly discussed: sprinkler controlled fire, fuel controlled fire, and ventilation controlled fire. Okay, you can look at the figure at the right, where it shows an ideal fire development. What happens initially? The fire starts, I mean, the material starts burning, which is the ignition, we call as growing stage. The fire grows. You can see TG. TG is the growth time. The growth time varies from the type of fire. If it's a slow fire, I have shown to you in the previous slide, it takes 600 seconds to reach 2000 kilowatts. The 1000 kilowatts is a number they are showing. It can be increasing based on the materials burning. Fast growth fire, the growth to 1000 kilowatt, which will be 75 seconds. So this is the growing time, which is called as TG, growing time. And after the fire has growth, it will continue to burn for some time in a steady state. Even in a T-squared fire, when the fire reached its peak, I mean the entire, assume a sofa, it started to burn at a corner. When the full sofa is burned, I mean, it starts to release the entire heat release rate. And then it continues to burn until the size of the sofa, that is called steady state. It will burn and burn. Then once the sofa's mass, it starts to decline, then the fire will not be giving it the same peak energy, then it will start decaying. That is called TD, TG, TS, and TD. So this is called growing stage, this is called steady state, QS, this is called decay stage. Decay stage will happen at 2 conditions. One, the mass of the sofa is finished, or you do not have sufficient oxygen to burn. So this is the ideal development case, where you have a proper ventilation within the building and there is no sprinklers, nothing. Generally, the fire is happened, this is what will happen. Or a fire happening in an open atmosphere, the same will happen. Will grow, will develop and decay. No external forces here. This is called as general fire growth. If the same fire is happening in an enclosure where you have sprinklers, the development will not be the same. What happens? Look at this bottom figure here. The fire growth, which is the growth time, the sprinkler starts to control the fire, because the sprinkler will be activating probably at 200 seconds, 300 seconds, sometimes 80 seconds, 60 seconds, depends on the growth rate of the fire. Once the sprinkler starts to control the fire, the steady state will not be continued. I mean, it's supposed to go higher okay, uncontrolled fire, then it should go horizontally to a steady state, then it should start decay. But what happens when you have a sprinkler system? The fire starts to get controlled by the sprinklers here. Then it will decay down because of the cooling effect of sprinklers. It is not the fuel completed. It is not the non-oxygen available. It is because of the sprinkler which is controlling the fire. This is called a sprinkler controlled fire. Here, okay, now you have, this is called sprinkler controlled fire, and this is called, the top curve is called fuel controlled fire. Here, what is the governing factor? Which is the fuel. So we call this fire as a fuel controlled fire. We call this fire as a sprinkler controlled fire. In your smoke management calculations, sometimes you need to consider fuel controlled fire. Sometimes you need to consider sprinkler controlled fire. We will be seeing when we should when we should use this terminologies when we are designing the smoke management system. Ventilation controlled fire, the third, which is not relevant to the smoke management system, but let us see. Fire growth depends on available oxygen, not fuel amount. So for example, if a fire is happening in an enclosure, in a space where you shut down all the windows and doors, what happens? The fires will still burn till the available amount of oxygen within the space. And once the byproducts of fire is released, which is the carbon monoxide, carbon dioxide, whatever it comes out of the fire, that will fill in the room and it will displace the oxygen. Okay, which is exactly, if you want to say the terminology, sorry, I cannot remember the terminology. It will displace the oxygen at the place. Then you will not have enough oxygen for in that particular space to burn. So this is called as ventilation controlled fire. Fire happens, you shut down all the doors. So there is no way that a fire can develop further because there is no oxygen available. But suddenly if you open a window, it will be a blast. Now, calculation methodologies. I do not want to take you into full calculation, but I want to explain you the way how to calculate. The first methodology of smoke control system I was explaining to you is a natural smoke filling. The slides, I mean, the images or the formulas, whatever you are seeing in the slides are taken from NFPA 92. It is not my own literature. So it is from NFPA 92. As you can see in the left side figure, this is called as right top in section 5.4.2 of NFPA 92, which talks about height of first indication of smoke with no smoke exhaust operating. So basically this, if you are using this system, I have explained to you before, there is no need of smoke exhaust system, but we need to ensure that the occupants can evacuate before the smoke comes down. How to calculate this? That is this formula. There are some restrictions for this, using this formula or this system. The major restriction is the ceiling should be flat. The ceiling cannot be in a irregular shape or it cannot be a sloped condition. It should be a flat ceiling. So if you look into this left side figure, it shows a building. The gray color, it shows smoke layer, and the bottom black line, it shows first indication of smoke. Below this level is called as tenable condition. And this is called hot smoke layer, and this is smoke layer interface. Here, there will be smoke, but it is not as dense as here. That is why it is called as transition zone. Slowly, this transition zone starts to come down to here. When the smoke develops further, the transition zone will be changing, and the smoke layer depth will also be increasing, and the first indication of smoke will be going down. So the term first indication of smoke is the first smoke which comes to the human tenable limit. Okay, when we can use this system? Where all the following conditions occur, the height of first indication of smoke above the fire surface, which is Z, I have explained you before, shall be calculated using either equation 2.1a or 2.1b. Why 2? One is in SI units and one is in American units. So the conditions here are, this should be uniform cross-section area with respect to height. I mean the smoke filling area. A by H ratios in the range of 0.9 to 14. What is A by H? A is the cross section of the smoke to be filled, this entire cross section. H is the total height of your particular floor or an atrium. And Z by H shall be greater than 0.2, which is the tenable height versus the total height of your particular floor. Steady fires, This formula is only for steady fire. We have another formula for T square fire and no smoke exhaust opening. So this is the formula. Here we need to interpolate this formula to get the T out here. Then only you will know the time seconds. I don't know why NFPA 92 has written like this. They must have given us one more formula to put the T here and to put the Z by H at this side. So we will know exactly, you can see T is time. So how much time we need to, we have for the smoke to come down. This is for T square. Also, there are conditions, uniform cross-sectional area, same. A by H square is up to 23, whereas in previous slides, it's up to 14. Z by H should be greater than 0.2. Here also greater than 0.2. Steady fires, no smoke exhaust operating. So again, this is the formula to determine the time required. Now I have made a sample calculation to make our life easier for the seminar purpose. Now let us take an example of this, an auditorium, because when we see this auditorium, we normally tend to say that smoke exhaust system is required, right? But do we really need to have a smoke exhaust system based on this natural smoke filling? Let's see. Now here what I have considered, I did not consider this seats. These seats are far away. It's a cross section. In this auditorium, only these seats are there. It's a cross section of another space, which will have some partitions. So assume for this condition, the seats, what you are seeing, the chairs, which is entirely at this level, okay, which has a height from here to the top approximately 22 meters to the top of the ceiling. You can see the red marking here. So the cross-section area of the plenary hall, this is the cross-section, the entire cross-section is 1,816 square meter. I am not taking the volume, cross-section. Total height of the hall, 22.3 from the base, the stage base to the top. Minimum tenable height to be maintained. I mentioned up to this point, which is 11.9 meter, which will not be working because the smoke will come down very fast. But we are considering for this level occupants. Conditions to match. So for the T square fire, we had 4 conditions, right? 5 conditions basically. It should be uniform cross section. The A by H square must be 0.9 to 23. Z by H shall be greater than 0.2. So in this example, I am matching all the scenarios. So first you need to check whether you are matching these conditions or not. Then move on to the formula. If you are not matching to any one of these conditions, then you cannot use the natural smoke filling methodology. So I have made an example here based on this. So as you can see here, the formula, so total time, I interpolated the formula here. So the total time needed for the smoke to come down at 1.8 meter height is 231 seconds. So within 231 seconds, the smoke will be entirely coming down just 1.8 meter above the floor level. So beyond 231 seconds, there is no more tenable conditions. So can we use this system? Yes. But before that, we have to see whether we can evacuate the occupants within that space. So an evacuation analysis is considered for the same area. The evacuation formulas are based on Society of Fire Protection Engineers and NFPA correlation equations. The total time needed for the smoke interfacing layer is 315 seconds. I mentioned here. Why I mentioned 315, whereas I'm showing here 231? Because it is the smoke descending time, the 231 seconds, whereas the smoke has to rise first up to the 20 meters, right? Which is called thermal movement from the floor level to the ceiling level. Then from the ceiling, it has to radially go at the side to the wall. Then only it will start to descend down. It is not the smoke goes up to some point, it will descend down. No, it will go and hit the ceiling because the buoyancy of the smoke will be higher from the surrounding air. The principle of, it's a physics principle. Basically, if you have a hot air, which is less denser than the surrounding air, it will rise up. The same scenario in the smoke, it will rise up. It's like we are seeing in a chimney in industrial facilities where hot smoke gases rises up, or for HVAC engineers, you can see the air comes out of the cooling tower. It is similar. It will go to a point, then it will scatter into horizontal way. So as long as the buoyancy is there, it will go up. Smoke, it will have a lot of buoyancy because of the heat energy created by the fire. It will go till the top of the ceiling, hit and come down. So it needs some time for the travel. That's why this 315 seconds has considered. This is also not my numbers. This is based on the Society of Fire Protection Engineers book calculations. So the total occupant evacuation time is conservatively considered as 276 seconds. Of course, we have software to do this. I will show you if we have time at the end of this session. Therefore, a smoke control system is not required in the plenary hall, as the smoke control system is provided for tenability during occupant evacuation only. If you look into our QCDD requirements or NFPA 92, the main purpose of providing smoke control is to have occupant evacuation tenability. If you achieve this, then why do you need to have a smoke control system? But the design of the system is so critical that you need to prove this via softwares. There are two softwares to be used here. One is Fire Dynamic Simulator, another one is called Pathfinder. Then it has to submit it to the Civil Defense Authority having jurisdiction. They have to approve this. Then you can use this system. The next methodology is mechanical smoke exhaust method. You people must be very familiar with this ASHRAE calculator, right? You will be all using this. But something to understand here. Okay. How many of you have used this software? I mean, this Excel sheet. Can we unmute can I request the host to unmute?
Yeah. So yeah. 1 minute.
I just want to learn from the participants that how many of them are aware about this this Excel sheet, or they can raise their hands.
Yeah, whoever they can raise the hand, they can unmute.
So we have two people.
No. Yeah, two people. Mr. Heba Nasser, yeah, you can unmute.
Basha, you are on mute.
Hi.
Yeah. I'm clear. Thank you. Yes, thank you. You can unmute yourself. I just wanted to know how many people are familiar with this, so that.
Yes, I'm familiar with this.
Very good, wonderful. Okay, there is a calculator which is released by ASHRAE itself. Okay, this is from ASHRAE, which helps us a lot to determine the smoke exhaust rate requirements. It is a very simple and useful Excel sheet. It's an Excel sheet. I will share this within the group. Of course, I'm a member of ASHRAE itself. I will share in the group. So you can see the formula given in NFPA 92. It's all given here. So what you need to input here, you can see the input here. You will get output directly. But you need to know the fundamentals. I have explained to you before what is Q, what is QC, what is Z, Z1, M. I hope you know this. If you have questions, you can ask at the last. Q. This is where we don't have sufficient informations at certain times. Sometime we have an information. So Q I have mentioned here as 4,000 kilowatt. So is the 4,000 kilowatt taken from where? It depends on the burning material, basically. What material is burning at that place? In the civil defense, Qatar civil defense requirement, they are giving us a guideline only for car parks. So you need to assume in a sprinkler controlled car park, 4,000 kilowatt is the heat release rate, whereas in the non-sprinklered car parks, you need to consider 8,000 kilowatt, which we call as 8 megawatts. This is the only guidance we have in the QCDD documents. We do not have any other guidelines. Some of the guidelines you can find from NFPA 921, which is the guide for smoke explosions, and NFPA 502 as well, which is a standard for standard for tunnel firefighting systems. I will explain you further how to select this value, but let us see now the difference between maintaining the smoke interface layer. I am assuming a Q, which is the heat release rate of fire, as 4,000 kilowatt, 4 megawatt. Okay. So I want to, in atrium, I want to maintain 15 meters. Why I want to maintain 15 meters? I need to see the top floor, which is the top communicating space, 1.8 meter above the space. Why the 1.8 meter is specified? Because it is the average human height. So the smoke layer shall be above the human height. So this 15 meters from here to the top, I'm considering including 1.8 meter of the occupant. And what is the makeup air temperature, TO, you are providing from here, which is 30 degree, I'm assuming. You can change this value as you require. Treated fresh air, some people you will be using, or direct, untreated fresh air, depends on the temperature. You can change the outside air. It has a small impact on the smoke exhaust volume, not a very huge, but a small impact. The amount of makeup air supplied is not mentioned here. It should be around 80 to 90%, as mentioned in NFPA 92. So, for example, here the total volumetric flow rate is required is 90.6 meter cube per second. So approximately 90% of this shall be supplied through the makeup air. Some people or some design, you might not see the makeup air, and they will say makeup air is available within the room. No, that is not the case. Makeup air must be introduced because it helps buoyancy also. So atmospheric pressure 1 bar, 1013,000 pascals. This is pre-filled. Ks is 1. What is Ks? You can see here. Ks is 1 for steady smoke exhaust. The smoke exhaust is not variable. It's a steady. Normally, the smoke exhaust will be steady. There is no variable frequency here. So steady smoke exhaust. They have mentioned here the number 2, for calculating the volumetric flow rate of smoke exhaust, a value of Ks1 needs to be used, except when other values supported by test data or an engineering analysis. So normally it's 1. X is 0.70. For smoke control design, a value of X, which is convective fraction, dimensionless, is almost always used. Any other value should be supported by engineering data. So when you use this value, you can see the convective heat quotient is 2800 kilowatt. I told you it is 70% of the Q. So when you multiply this 70%, you will get this value. Z1, leave it, which is called limiting elevation, which is the minimum smoke layer height. TS, which is the temperature of smoke layer temperature here, which will be 60 degrees Celsius. You must be wondering, how come the smoke layer temperature is 60 degrees Celsius here? It should be more, right? Generally, because smoke means normally the fire generates 500 degrees Celsius, 400 degrees Celsius. Then how come the smoke will be 59? Because this calculates the atmosphere temperature as well and the height of the smoke layer interface. So the smoke layer temperature will be merely 59 degree only because of the Z height you are telling. What you said, you need to maintain 15 meter clear height. So when the smoke goes up, it loses its energy as a convective heat transfer. That's why the temperature of smoke is less. So do not worry that the temperature of smoke shown is very less. And this is the density of the smoke, 1 kilogram per meter cube. And this is the volumetric flow rate, 90.6 meter cube per second. Here, what you can see, M, which is the exhaust mass flow. The smoke, how much smoke is coming is exhaust mass flow, which is 96 kilogram per second. When I want to convert into volumetric flow rate, which is the fan size, which is V, which is 90.6 meter cube per second. Now, the same atrium, I want to keep a different height. Okay, so see, I use the same parameters, whereas I use 20 as my limiting elevation. So not limiting elevation, clear height, 20. Look at the fan capacity now, 138.9 meter cube per second, because the fan needs to work more to extract it more so that it can maintain 20 meters clear rather than 15 meters. So the volumetric flow rate is 138.9 meter cube per second. The mass generated here will be 152.51 kilogram per second because of the smoke layer depth. So this, if you change the Z value here, the amount of smoke, amount of flow rate required for the fan will be varying. So we must be careful about selecting the Z value. In a car park, normally you will have a 3 meter ceiling. If you want to maintain a clear height of 2 meter, the extraction fan capacity requirement will be different. If you want to keep 2.4, the extraction fan capacity will be different. That we will discuss separately in our car park area. Okay. Now, guys, with this figure, what you can understand, if I can provide a smoke extract as this volume, 138.9 meter cube per second or 90.6, a smoke extract fan, one number at the top with an outlet, it will be working, right? Yes, it should work, but this is not how the code is telling, or this is not how the smoke behaves. If you keep only one smoke exhaust fan or one smoke exhaust outlet, you will be ending up failing the system. There is a concept called plug holing. This is called plug holing. Plug holing means it's a direct draw of smoke into an exhaust inlet, bypassing the surrounding smoke layer. So you can see here, it still extracts, but it doesn't extract properly. I mean, it's like a conical space. You are just extracting from one point, which is called as plug holing. It occurs when exhausts are too close to the smoke layer interface, creating localized flow and poor smoke removal, result in inefficient smoke control and may compromise tenability in other areas. So you need to know how many fans I need to use. Okay, the total volumetric flow rate is this much. Can I achieve by one fan, or do I need multiple fans, or one fan with one out, one inlet, or one fan with multiple inlets? Sorry, multiple extracts. NFPA 92 recommends placing inlets well above the smoke layer and using distributed extraction to prevent it. That is called plug holing approach. You cannot just have one extract or two extract and will say, and even the smoke extract size is 4 meter square opening, this will not work properly. Let us see the concept. This is also again given by the ASHRAE calculator, but this all we are going to see now in the analysis. Look at here. Here, this is the inputs you need to provide in this one. QC, you need to use QC value here. So this is why I was explaining what is QC. So you need to understand this is the convective heat release rate, which is 70% of the Q. Here you will not use Q directly because this is not dealing with the fire directly, whereas it deals with the convective heat of the fire, which is away from the fire. So 2800 kilowatt, I am using the outside air temperature of 30 degrees Celsius. Mass, you need to take from the old Excel sheet how much mass you want to extract, volumetric flow rate, how much, and this is the most important parameter. This one you need to understand. If you do not understand and if you apply, the smoke system will be failing. This one you cannot determine by the hand calculations. D, I mentioned 3 meters. What is D? 3 meters. Look at this figure here. This is called D, where I have the exhaust outlet. Okay, from there, what is the height of the smoke layer I am allowing to develop? Basically, if you see in this figure, this is D from here to the top. Okay, so that is D. So I mentioned 3 meters. Then I mentioned this is all constants, this 2 value. And here A and B is the diameter, sorry, the area or the length and breadth of the rectangular grill. So A 1 meter, B 2 meter, and I mentioned 13 number of inlets. It says check 1, check 2. The requirements of note above 4 is satisfied, 5 is satisfied. What is 4 and 5? D by DI. D, the small d, which is the total height. DI, which is given here, effective diameter of the inlet. It shall be greater than 2. And VS must be greater than Vmax. What is VS? Volumetric flow rate of one exhaust inlet. That is VS. That must be greater than, sorry, must be lesser than Vmax. If it is not, it will cause plug holing. Now, look at this here. The same I'm using here. Now, a designer is using the wrong values. D1 and A as 1 and B as 1 and putting 2 exhausts. Will it work? We may see in a normal way, yeah, it has to work, but it will not work. It shows the requirement of note above is not 4 is not satisfied, 5 above is not satisfied. What is 4? The D by DI must be greater than 2. Why it is not matching? Because D, you are mentioning only 1 meter of height, which will not work. It needs at least 2 to 3 meters, the smoke layer height for large atriums. And the number of inlets. What is number 5? It is telling Vs must be less than or equal to Vmax. Now, if I'm using 2 inlets only, it will not see, each is taking 69.5 meter cube per second. So the combination of 2 will be higher than the original volumetric flow rate I need to take, which is 138. So which is not acceptable. So look at the difference here. It needs 13 extract outlets. So basically what you can have 13 small size fans, which is very costly, but you can have one extract fan ducted into 13 extracts. Here, if you do this, it will not work. Now let us see this example in the CFD analysis. I mean, I have made some examples for you to understand what we are telling, whether it is a reality or not.
Whatever, sir.
Can you see my screen?
Yeah. Go ahead. Which one? The same screen?
Yeah, which is a model screen. Can you see? It's not a PowerPoint.
No.
We are
Okay.
still on your presentation, sir.
Yes. Wait. Okay. I hope you can see.
Yeah. Now is okay.
Okay. Now this is an atrium. 1, 2, 3, 4, 5, 6 floors. This is the top slab. Let me hide this slab. Oh, probably I cannot hide from here because, okay. See this. This is an open atrium. As you can see, these are all communicating spaces. Okay, and I positioned 4 sofas here. And if you see the exhaust, I have placed 4 exhaust here. You can see the highlighted figure. Exhaust 1, exhaust 2, exhaust 3, exhaust. By design, you can see it is very great, right? So it should take the smoke out. But in reality, will it take smoke? Let's see. This software is called a Pyrosim, Fire Dynamic Simulator. You can analyze. This is called, otherwise called a CFD analysis. So okay, we will slowly see. This is burning, right? And the smoke hits, as I told you, it first hits the ceiling. You can see the phenomena, how it's developing. As I told you, the smoke will not disperse radially out. It has to hit the ceiling first. Then it will slowly starts to come down. The green color line I mentioned is the 1.8 meter height, tenable height. So my extracts are running, basically, all the 4 extracts are running. You can see the velocity of the extracts, which is around 3 meters per second, which is the extracting. But my smokes comes down. I'm not having the tenable environment. Let's see, I will show you when it goes down full. Okay, a simple thing is I can show you the slice. Suit visibility, I have, this is the visibility. I mean, how much visibility you have in the top. So if you look at the visibility, it's 2.5 meter and it's very close. I mean, at 288 seconds, you see it's a full blue. There is no visibility. The smoke starts to spill down. If you continue, you see the smoke at the next floor also. This floor is disaster already. So there's a full of smoke. And I stopped the simulation because I do not have time to run further. But with this condition itself, it shows you can see there is no velocity. Sorry, I mean the viscosity. I mean, you can see this is the visibility. Basically, the visibility is dropped down almost at 300 seconds itself because the extracts are not working properly. This is the reason basically. Now the same model. I have run in another scenario. Wait, I will share my screen. Just give me a moment. Okay. You can see the screen, right? The new screen. Yes, the same model. I'm going to hide the top mesh and I'm going to hide the Okay, here I have placed several exhausts, which is 13 exhaust. I put 14 basically. You can see this all exhaust at the top. These are all exhaust, and I have increased the smoke reservoir depth. You know, we discussed D distance in the last simulation. I have used D as 1. Here I have used D as 3. So we need to give enough depth for the smoke layer as well. It is not that I have a fan, so it should extract. It will extract, but it will not give you that enability. Because this is what we think generally as a mechanical guys, right? I have a fan, I have a flow rate, it should extract. That's the design, but it will not. You need to give the proper height also. So here I have allowed up to this height, which is the D in the Excel sheet. Now let us see here what's happening. You can see the smoke is, fire is developing, right? And you will see, basically I activated this, you will not see the exhaust here. Why you will not see the exhaust here is, I put a control that it should act, the fan should operate after 50 seconds. Why? Because the smoke detector has to detect, right? Then only the fans will operate. So up to 50 seconds, you will not see the exhaust outlets. Just wait. After 50 seconds, you will start seeing the exhaust outlets, because this is the real scenario. We need to run by real scenario. That's the, you can see now, the exhausts are being showing. But if you look at here, you will not see. So let me run it fast. So the smoke is coming. You can see the visibility. Okay, you have a very clear visibility in at 1.8 meter. You can see there is no smoke. The smoke, what you are seeing is the smoke at the middle, not at the, not at the walkways. Whereas you can check this here. You have a good visibility all around. And there is no smoke comes down at this level. The smoke, what you are seeing is the middle smoke. If you want to see, it's the middle, basically. It's not at the side. So this area is clear of smoke. This is the importance of plug holing. And plug holing is related to the depth of the smoke layer and the number of exhaust outlets you need to be modeled in your design. Okay, let's go back to the slides. I hope the concept is clear at least. So this is the importance of considering the plug holing and the fire values. So we have seen this analysis. Now, heat release rate. Now let us go to the point Q, because it is not normal for you guys, for HVAC persons. Of course, I was doing also HVAC. I just changed my profession into FLS. I was doing FLS, but now only into FLS. Previously, I was doing full mechanical. So as a pure mechanical guy, you will have a limited information on the fuel which is going to be burned or the fuel parameters. Some peoples you might be having, some peoples, most of the peoples will not have the information. So I have explained to you what is heat release rate, which is the speed at a fire which releases the energy. You can see some data which is taken from NFPA 502. This is for tunnel fires. You can see passenger car fire, peak HRR, time to peak, representative HRR. You can see 8 megawatt or 5 megawatt, buses 25 megawatt, heavy goods trucks 200 megawatts, flammable combustible liquid tankers 300 megawatts. So this is the type. So if you are designing for a car parks, we have the ready data, right? Car parks or bus park, everything we have. If you look at another table, which is taken from NFPA 902, which is a standard for fire and dust explosions, you have some other inputs as well. Waste baskets, how much will be the HRR? Cotton matters, how much will be the HRR? TV sets, how much will be the HRR? So you can have all this information. Now, if you don't have the information of a material which is about to burn, what we can do? We can assume? No, we should not assume. Assuming will go wrong, because if you assume the wrong Q value, the smoke exhaust system is going to fail. If you're designing for a higher one, wonderful, but it's again not advisable. But if you are designing for a less Q value, the smoke extract system is going to fail. So what we can do in this situation? You can see here, defining heat release rate, which is Q, for unknown materials used in the space. Similar enclosures test data from NIST, which is called National Institute of Standards and Technology, USA based, or FM Global, which is an insurance company document, or research papers, and get approved by AHA. You know, for example, you are designing a proscenium stage, a theater kind of a setup. You don't have anywhere it's mentioning what is the HRR for a theater, as we have seen in the tables. Maybe your civil defense will be giving you these values, but our civil defense doesn't have this value. So what we can do? We have to search in NIST or FM Global, because they are third-party agencies where they are doing testings at several laboratories to see what is the real Q values required. You can take from there and submit to the civil defense and get approved in your DC1 stage, I mean the beginning stage. Or if you don't have, and if you don't know what is going to be in that space, for example, you are building for a tenant, he tells, I want a stage. Okay, fine, stage. But what is going to happen in a stage? It's going to be a music concert stage, or it's a film screening. We don't know anything, right? So we don't know what materials are going to burn also. So if we don't know what materials are going to burn, then how we can design a smoke management system? That is where Alpert's correlation equation is coming. This Alpert's correlation equation is taken from SFPE handbook, Society of Fire Protection Engineers handbook, volume 3 and 5. It helps us to determine the Q value by a different way. What is a different way? This will work only if you have a sprinkler, which is called a sprinkler controlled fire. We have discussed in the previous slides before. I told you fuel controlled fires and sprinkler controlled fires. Alpert correlations should be used if you have sprinklers in the space. What if you don't have sprinklers in the space? You have to consider a fuel controlled fire. You have to somehow take a data or somehow doing a simulation to determine how much worst case scenario you have to take. For example, you are designing for a stage, you have to see what is the worst stage in the real life scenario. You have to find a value for this and do the smoke management system calculations. But if the space is protected by sprinkler, the life is very easy. We can find out the Q in a reverse way. And this is an approved way. I mean, I do not want to say reverse way. This is an approved way. So what is Alpert's equation? Alpert he's a gentleman engineer like us. So he created some equations to determine the ceiling jet airflows, the activation temperature of sprinklers. Alpert's equation can be used for steady state fire as well as T-squared fires. So it assumes a quasi steady state fire, because I want to discuss with you the T-square fire, which is called as quasi steady state. A fire that grows gradually, allowing ceiling jet conditions to be treated as momentarily steady, used to estimate, this is the important thing, used to estimate the temperature rise and velocity of ceiling jet, a key input for sprinkler and detection activation time. So what are we trying to do here? We are going to see what is the activation temperature of a sprinkler in a particular space. Then based on this, what will be the growth rate of the fire at the time of sprinkler activation? Because normally, why are we providing sprinklers? To control the fire, right? Sometimes it will extinguish as well. So when you start to control the fire, what happens? Your HRR will not continue to grow further. It will decay down because of the cooling effect of sprinkler. So this is a good point, that the sprinkler activation time corresponding the HRR values can be used to define the smoke management system calculations. This is called Alpert's correlation. Okay, now again, we go to calculations. I have made some Excel sheet for you, ready Excel sheet. This is for me, basically. I will share with you guys in another, a web page, and CFD analysis based on that. I'll share you the screen shortly once I opened. Okay, this Excel sheet is prepared by me. I do not want to give credit to someone, it's by me. Okay, so this T-squared ramp, you can take this from a website, which is called UT Square Fire. I will give you the link. Just go there, put the values, and you will get the heat release rate curve. So it shows for a fast growth T-squared fire, fast growth T-squared means at 150 seconds, it should reach 1000 kilowatt. You can see this line here. So what I have told this Excel sheet is, the values of what I have used is, I am assuming a 4 megawatt fire. I'm assuming, just assuming a 4 megawatt fire is going to be happen here. Assume a car is going to burn such a huge in a stage. So give me the time values and HRR corresponding values. So this software, it's a website which gives me this curve. So I have interpolated the graph into the time and HRR values. You can see 10 seconds, 4.7 kilowatt. So it goes further up to 4 megawatt. At 290 seconds, it reaches 4 megawatt. So this is the growth of a fast growth fire. These values will be changing for a medium growth, slow growth, ultra fast, everything it will be changing. So how we can determine? There are formulas. These are the formulas. This is called U is called sealing jet velocity. This is the detection activation. Sorry, detection, not detection. Heat detector activation time or sprinkler activation time formulas. So what we need to mention? We need to mention the ambient temperature here, 30 degrees Celsius. Radial distance to first sprinkler. You are going to assume the fire is happening at the middle of the stage. Of course, you will be locating the sprinklers in the ceiling by 4 meter by 4 meter grid, right? Light hazard, or 3 meter by 4 meter for ordinary hazard, or 3 by 3 for extra hazard. So you can change this value. Now assume we put 2 meters, okay, next to the fire. Height of the ceiling above the fire. How much is the height of your ceiling? I am gonna assume 15 meters, okay, 15 meters. What is RTA of sprinkler? Response time index, basically. Normally, it's 50 for quick response sprinklers and 80 for standard response sprinkler. Assume I'm going to use quick response sprinkler. That is what the quick response is, a thinner bulb. You can see the two types of bulbs in a sprinkler. One is thinner, one other is thicker. Thinner is quick response, thicker is standard response. The diameter is 3 millimeter and 5 millimeter. So I'm going to use the 3 millimeter one. So when I put this value, you need to know what type of sprinkler you are going to use. What type means in terms of temperature. So normal temperature to be used within the building is 68 degrees Celsius, right? So I need to see the TD, which is the detection temperature, where it is reaching to 68 degrees Celsius with this condition. The heat is developing, sealing jet velocity is here, whereas the temperature goes here. So if I go down here, I am reaching the activation temperature of sprinkler 68.2 degrees Celsius at 240 seconds after the fire starts to grow. Then what is the growth rate of the fire at the time? 2.7 megawatt. This is the Q value you need to consider. Now, if the ceiling height is changing 5 meters, of course, the value will be reduced. The sprinklers will be activated at 130 seconds itself. The HRR at the time of sprinkler activation is 792 kilowatt, which is 0.7 megawatt, considerably less than the previous example. So with this way, you can change this values. Time versus HRR depends on the T-square ramp. Based on the medium growth fire or a slow growth or ultra fast, whatever, you can change these values and you can input this value. So it will give you the activation time. Okay, now I will show you in a web page. Okay, someone had did this. I am not doing, I did not do, so I don't want to take credit. It is someone did this. That's a very useful. I'll share you this. Really, someone did a very wonderful job. Tanveerhassan.com. Okay, this is a simple web page. You can see here schematic of sealing jet governing equations, the same equations, whatever I was using, graphical data. Okay, let's see now. Now here, he's asking some inputs. First, you need to put the RTI, which is the response time index. You can put 50 or you can put 80, depends on the type of sprinkler you are using. Let me put 50, quick response. Height of the ceiling 3 meter. Let me change to 6 meter. radial distance from the sprinkler. Let me put 6 meters, 6 meters away. Fire growth rate, alpha. So here, click this. You can see the same what I was showing you here. It is given here. So you need to see what is this. Medium growth fire, fast growth. Let us assume it's a fast growth fire, 0.047. This is the value you need to put, 0.047. Activation temperature of sprinkler is 68 degrees Celsius. Ambient temperature is 25 degree. Time step. You know, what is this time step? Time step, it's required in a quasi-steady state or t-squared growth, because at every seconds, the fire growth is different. So I am telling the software, count me for every 10 seconds, what is happening. And I am telling the software, check it for 500 seconds, where it is the activation happening. So I just click calculate. So I can see here, it is activating at 299 seconds, the 68 degree, and the fire size at the time will be 4,202 kilowatt. Okay, again, if I change my ceiling height here to 15-meter atrium, I need to increase here, because why it is showing 0? Because the growth rate needs to be increased. Maybe it will reach at some, we don't know. We will see here. Yes. See, it reaches at 575 seconds. You need a HRR of 15 megawatts. It's like a bus is burning. Then only the sprinklers can activate. If you want to use the Alpert's correlation equation to find out a medium growth fire, not medium, fast growing fire, because 0.047 is fast growing fire, and a sprinkler located at 6 meters needs 575 seconds to activate. At the time of fire, at the time of 575 seconds, the growth rate will be 15 megawatt. But if you put the sprinkler closer, I mean, don't put very far. I mean, you change your design, because 15 megawatt seems very high and you need a huge extract fans. So let us put the sprinkler at 3 meter distance from the fire. You need 7,558 kilowatt, half of that value. So now if you further reduce the spacing between the sprinklers, okay, normally sprinklers needs to be spaced at least a distance of 1.8 meter between the sprinklers. So you can put 2 meters also. So you are still reducing 6,680 kilowatt. So 377 seconds, sprinkler will activate. 680 seconds, sorry, 6,680 kilowatt is the fire size. But can we take this blindly? I would say no. Why? Because based on one sprinkler activation, defining the Q value is really not a conservative approach, because such a 6 megawatt fire cannot be controlled by one sprinkler. One sprinkler can take a maximum of 800 kilowatt to 1 megawatt of fire at a ceiling distance of 3 meters, at a 3 bar pressure basically. So if the ceiling height is getting increased, the velocity of the water comes from the top will be disturbed at the bottom before it reaches to the fire plume. So I would say at least 4 sprinklers around the fire should be activated. Then I will freeze my HRR. This is the concept. This is a very conservative approach, because 4 sprinklers around the fire is well enough to control the fires. Okay, now let's see some simulations again. Okay, I assume a big hall, 20-meter high, and I put a fire here, and you can see sprinklers. I mean, pendant sprinklers are perfectly fine. Do not think that you need to have an upright sprinkler only. Pendant sprinklers and upright sprinklers both does the same job. It depends upon what location you want to use. Now I have assumed a medium growth fire. Okay, medium growth fire. Then I want to see whether the sprinklers are activating or not. So let me show you. The fire grows. But surprisingly, in this simulation, none of the sprinklers are getting activated till the smoke completely comes down and make disaster to the occupants there. So what is the purpose of having a smoke management system if I allow the smoke completely to come down? See, the fire is burning. It's a medium growth fire. Since the ceiling is very high, it cannot take the fire. So I need to change my fire load. I mentioned 4 megawatt. I was considering 4 megawatt. So I need to consider 8 megawatt to see at what time it will activate. So when you are doing this, simulate Alpert's correlation equation, you need to consider the biggest fire possible to happen in that area. I assume 4 megawatt. Here, not 4 megawatt, I use 2.5 megawatt. Now, I will show you another simulation for the same area where I considered 5 megawatt fire.
Yeah, you're sharing your screen.
No, not yet. I'm doing. Okay, you can see here the same room, but I used a 5 megawatt fire. Now let me put the. Okay, here also the same. You can see sprinklers. It's a 4x4 configuration, 4 meter by 4 meter. Now here also smoke is coming. Still, I have some clear height here. Still a little bit. Let me see the sprinklers are activated or not. Not yet. See, it activated at somewhat 440 seconds. What is the smoke density there? Oof, it's full. So still I use 5 megawatt here. So I need to use more because the height is more. So by considering Q as 5 also, it is not working by using Alpert's correlation. Alpert's correlation, you have to use the CFD analysis also to check whether the smoke is traveling down or not before you activate the smoke extract system. No, at 440 seconds, still it did not. Just now the sprinkler got activated, the water still not reached here, but the smoke is already down. So the fire size, what we need to consider in the Alpert's correlation equation should be way bigger. So just assume, see now 2 sprinklers got activated. Okay, now when the time goes further 3, so you can see around 4 sprinklers will get activated at 500 seconds basically. So 550 seconds, around 4 sprinklers got activated. So what I should take the HRR corresponding to 550 seconds. And I need to have a CFD simulation also to ensure that at that 550 seconds, where is my smoke layer? It should not be full. If it is full, then there is no point of designing smoke management system. This is the problem when you don't know the Q value of the fire. It will happen at many places. Some of the designers they mention 5 megawatt as a fire load and they design the smoke management system. You look at this figure, what happened to 5 megawatt? It will activate. The sprinklers will get activated, the smoke will come down, and eventually the fans will work. But when it will work, when the entire space becomes untenable. But smoke detection systems are there. It will activate the smoke notification, fire alarm notification devices for the people to take out, but that is not the concept. Then we do not need to have a smoke control system, right? When the occupants can evacuate, then why we need to have a smoke control system? It is to maintain the tenability all the time during the evacuation. So you now understand the importance of doing the Alpert's equation along with the CFD analysis to see what's happening in a real picture. This is mostly important if you don't know the Q value. Now let's go back to our slides and we'll finish the remaining areas. Oops. Okay, so you now understand how this Alpert's correlation equation works. Okay, the last topic for today's session is car park smoke control systems. Of course, everyone are well aware about this, but I want to just give you some some inside informations mentioned in the course. We have, car parks can be defined as two types: open car park and enclosed car parks. So this figure, it shows, is that an open car park or an enclosed car park? By seeing, you can say it's open car park, but to qualify this as an open car park, some openings sizes must be maintained. Each parking level shall have wall openings open to atmosphere for area of not less than 0.4 square meter for each linear meter of its exterior perimeter. You need to have such openings. Such openings shall be distributed over 40% of the building perimeter or uniformly over two opposing sides. Why two opposing sides? Because the smoke, not smoke, the air from the outside will go into the fire area and which will take the smoke out of the other area. That's why the opening shall be distributed at two sides. Interior wall lines and column lines shall be at least 20% open with openings distributed to provide ventilations. This is the definition. If you have this, then it's called as open car park. If you do not meet any of this requirement, then it is not called as open car park structures. It is classified as enclosed car park structures, which will warrant mechanical smoke ventilation, sprinkler systems. Of course, now sprinkler systems are required for open car park structures also. Previously, it was not required. What is the ventilation requirements? Open car park, we do not need anything because it's open. Whereas if it's an enclosed car park, as per NFPA 88A, requires a minimum flow rate of 300 liters per minute per meter square of floor area during normal hours of operation. Remember, NFPA 88A doesn't tell you to have a smoke extract system during the fire mode. It is we engineers created. NFPA says 300 liters per minute per meter square of floor area during normal hours of operation. They never say use 6 air change, use 10 air change for normal mode for the fire mode. It is from British standards, BS 7346. This is what our QCDD is following. Mechanical ventilating system ductwork shall be in accordance with NFPA 90A. Ductwork shall be of non-combustible material. Okay. You can see this is the QCDD requirements. Above ground car parks, open car parks. The open car parking shall justify that no smoke stagnation will occur, such as from fire located somewhere in the middle of the car park. Otherwise, mechanical equipment that will aid in effective dispersal of smoke shall be provided. Open car parks, you do not need to provide smoke ventilation system, but if civil defense asks you to prove, you have to do an analysis to prove that there is no smoke stagnations. Above ground enclosed car parks, depends on the area. If the area is less than 2000, some requirements. If the area is more than 2000, some requirements. Like you can have 3 types: smoke vent system, which is the openings, flaps, mechanical smoke purging or clearance. Purging clearance means it's a post-fire event. Okay, it is not the jet fan systems. You are clearing the smoke after the fire event. That is called a smoke purging also. Engineered smoke control system, which is the thrust fan or conventional smoke control system using the duct fans. QCD requirements of below ground car park: aggregate flow rate less than 2000, smoke vents is allowed. It is not that you need to have always a jet fan systems or a bigger fans. You can have a smoke system also if the aggregate floor area is less than 2000. Suppliers, please excuse me, because this is what the code says. Normally, we used to provide smoke ventilation systems for all size of car parks, like 1000 square meter car parks. Also, we used to put the jet fans and put extract fans and make a festival over there. But we do not need, if you have a smoke vent system, if it is less than 6 meter deep car park, that's enough. I will explain you how it is. You can have a mechanical smoke purging, permitted. Engineered smoke control is permitted. I am not telling you should not use a jet fan system, but you have a cheaper option, smoke vent system also. Aggregate floor area which is greater than 2000 square meter, then yes, now we cannot make we have to make a party. We have to make the mechanical smoke control system. We cannot rely on smoke vents. Here you need a full engineered control system. Permitted, required. Natural ventilation. Okay, this is, I do not want to go into full depth, as you people are very well aware about the QCD requirements. So this is the natural ventilation arrangements, how it should be. This is the smoke vents to be provided at the top. How the smoke vents to be provided? Like this. This is how underground car parks less deeper than 6 meters, lesser than 2000 square meter area, you can have such arrangements. This is reference from NFPA, QCDD. So you can have a duct without a fan. It can take the smoke out. You have a duct without a fan at this level, separate levels, and a normal shaft to take the smoke out. This is more than sufficient for QCDD. But if they ask you to provide with a CFD analysis, you have to prove. So the main concept why they allow the natural ventilation system is lesser than 2000 square meter car park. You may have a question, why they allow then why do I need, if it is more than 2000 square meter, I need an engineered smoke control system. The concept is pretty simple, because in 2000 square meter car park area, the number of occupant is going, I mean, if it is 2000 square meter, you will have certain rooms also, like MEP rooms, other rooms, this rooms. So the effective area of the car park will be around 1000 to 1500 square meter, not 1500 square meter car park area. In this, if you take the occupant load calculation as per NFPA 101, it will be around 50 guys, 60 guys max. And this 50 guys and 60 guys can evacuate easily before this condition becomes untenable. Because if a fire happens here, the smoke has to rise up and go down, and it needs around, example, around it needs 150 seconds to 180 seconds to come down. So within these seconds, these people can escape. Whereas in the bigger car parks, there will be more number of peoples. So behavior of the people will be different, crowd will be different. We call as crowd management system. So if the number of occupants are more, the behavior of the crowd, everything is going to be different. There, you cannot expect the natural ventilation to give you the sufficient enability. That is the reason basically. So if your client doesn't want to have this natural ventilation, you should still go for the mechanical smoke extract, or if the civil defense feels that it is required, you still have to go. It's authority having jurisdiction requirement, but we have an option in QCD. You can see this is also acceptable. Natural ventilation with exterior openings and shafts. It's all by QCDD. You do not need to have any kinds of fans, but subject to the deep requirements and depth requirements and the area requirements. Mechanical ventilation system. This is the fans. By using fans, we have two types, as you know very well: conventional smoke extract, which is used by ducting system, and impulse ventilation. Impulse ventilation system, which is by using jet fan systems. So mechanical ventilation shall be provided for car parks located below ground or an enclosed floor area of more than 2000 square meter. I told you the reason. This is the reason why they're asking. So what it should do, the system shall, this smoke extract system or smoke purging system shall be designed for smoke clearance with the following objectives. This is for conventional ducted system. That's why this word smoke purging is here. Maintain smoke layer within the smoke zone to not lower than 1.8 meter from the floor. Contain the fire within the smoke zone or area not more than 1000 square meter of the center of the fire. This is the only place where they are telling to use 6 air change and 10 air change, because this whole concept is derived from BS 7346. It is not from NFPA standards. So guys, when you refer to the QCDD standards, when you see 6 air change, 10 air change, it is British standard, not NFPA standards. So each smoke control zone shall have its own extract fan or purging system. The system shall be arranged that the required rate of smoke zone does not fall below 50% in the event of failure of any fan or group of fans in the system. And the inlets and, the smoke extract inlets, they say, or extract, whatever you can say, it's all smoke exhaust, because the exhaust here itself. So inlet or extract here doesn't matter. It's both referring to the same. It should be arranged 50% at high level, 50% at the low level, distributed over the entire car park. But there is an exemption for residential building. You do not need to have the low level exhaust. You can have only high level. It is also mentioned in QCD standards. So it is not always that you need to drop down the duct till the low level to take 50% from here and 50% from there. There are few requirements. They're telling you need to place the smoke exhaust outlets. No portion in the car park must be farther than a 12 meter to a smoke exhaust, and it should be discharged outside 5 meter away from any air intake opening. This is normal HVAC, guys. Even for a fresh air design, we do like this. We will not put the extraction system, extract point where we have a combustible materials or flames, fumes. You will keep the minimum distance 5 meter, 3 meters. And the ventilation fan shall be fire rated for 250 degrees Celsius for 2 hours, or exhaust ducts for the car park smoke purging system or this smoke control system shall be a minimum of 1.2 millimeter thick heavy gauge steel. Why they mentioned this? Because 1.2 millimeter translates into almost 2 hours fire rating. You can say nowadays we have fire rated ducts without paints, without any kind of, I mean, we used to have SFRM, spade resistance material, or some kind of coverings. Nowadays, you can see bare ducts also as a fire rated duct. The concept is the thickness of the steel will have some inherent fire resistance capacity. So this is an example layout. As you can see, there are the red color is the exhaust. It is located at I mean, if you measure, it will not, no place of the car park is exceeding 12 meters. And this is the fresh air supply system complying to QCDD standards. This is an example. Here you can consider a velocity 8 meters per second, 9 meters per second. Do not worry about the velocity here because it is going to operate only in the fire mode. So the sound requirement is not going to be a concern. You can reduce the duct size as much you can, but do not go more than 10 meters per second. It will have a very weird noise. So you are free to select the velocity as you require. It is, you are not constrained here because nowhere it is mentioned that the velocity should be within this limits. If it is inside the building, the extract is passing on some occupiable space, that's a different case. But it's a car park, open car park, and it is going to operate only in the fire mode. So velocity is not a concern here. So you do not really need to have a very huge ducts. Okay, here is the important thing, mechanical ventilation requirements for jet fan simple system. This jet fan system also can be designed for smoke clearance as well as smoke control. You can see system designed as smoke control, smoke clearance. What is smoke clearance? I told you before, it is a purging system. Means the system operates after the fire to clear the smoke out of the area. Okay, so there is no tenability requirements here. There is no temperature requirements for occupants. If you look at these requirements of civil defense, they say if you are using a smoke clearance system, when you are clearing the smoke, the visibility upstream of fire not less than 10 meter, maximum air smoke temperature 400 degrees Celsius along the path to exhaust, at least one viable routes for firefighters from external is available within smoke locked area. Because why they're telling firefighters 400 degree, you can see, you can understand from here, civil defense allows you to have this kind of system also. You do not need to have a smoke exhaust system running during the fire mode. You can design for a smoke clearance system, but they will ask you one thing, if you want to use a smoke clearance system, prove that the smoke will not come down before the occupants are evacuating from the fire zone. System designed as smoke control. So here, now let's go back to the first slide we started. What I said about smoke control? There are two systems: smoke containment, smoke management. So here is the smoke management they are talking. Smoke clearance is not a smoke containment or not a smoke management. So the definition itself, we need to understand it very clearly to analyze or interpret what they're asking. So here, if you see, at 1.8 meter above the floor level and within 10 meter radius of the design fire, the following shall be attained during the first 20 minutes. You need to have 10 meter visibility. Again, 50% of the fans should, I mean, smoke is contained within defined zone boundaries or not more than 50% of the equivalent zone. I mean, within 50% of the car park, the smoke should be contained. Visibility should be 10 meters on all areas. Maximum temperature 250 degrees Celsius along path to exhaust, and all other areas outside the smoke logged area not exceeding 60 degree. Why? Because it is smoke management system. We need to have a tenable conditions. Whereas in the smoke clearance situation, they did not ask you this. They ask you visibility for the firefighters. The space in the car park shall be divided into smoke zones. This is all general things, you know. They mentioned here 4 megawatt for car parks protected by supervised sprinkler system, 8 megawatts not protected with supervised automatic sprinkler system. Now, I hope you understand why they're asking 4 megawatt and why they're asking 8 megawatt. I will tell you the reason. Of course, it is all related to Alpert's correlation equation, the ASHRAE calculator, whatever we were using now. See, when a car typically burning, I showed you a HRR, peak HRR from NFPA 502. It can be anywhere from 4 megawatt, 8 megawatt, 10 megawatt. We don't know, depends on the car. Sedan cars, SUV cars you have nowadays, EV fire cars are there. Now, so why they are telling 4 megawatt in case of supervised sprinkler system and 8 megawatt in case of non-supervised sprinkler system? Because whatever the fire, when there is a sprinkler is present, the sprinkler will take control over the fire. So at the fire of 4 megawatt, I mean, when the sprinkler takes the control of fire, the fire growth rate at the time of sprinkler activation will be well below than 4 megawatt. So the extraction system, if you design for 4 megawatt Q value, it will be working very good. If you don't have sprinklers, you have seen this Alpert's correlation equation simulations. What will happen if the fire is more? If there is no sprinkler, the anticipated growth of the fire will be very high. So that is why 8 megawatt. So your volumetric flow rate required for 4 megawatt will be different and 8 megawatt will be different. This is based on the sprinkler activation time. This is why they mentioned the sprinkler activation time. I told you, if you don't know the fire Q value, you have to simulate it a different condition. Okay, simulate it for 2 megawatt, simulate it for 3 megawatt, simulate for 4 megawatt, and see at what time the sprinkler activates and what is your tenability conditions at the time. So they have made their study and they have given us 4 megawatt and 8 megawatt as a reference. It's a very good reference, basically. So this is a simple, I mean, I do not want to take more time. This is a simple of a CFD analysis, but this is done in another software called ANSYS. You can do in ANSYS also. Pyrosim and ANSYS both are available to do. So here, if you see, there are 3 jet fans at the top, 1, 2, 3, and this is the extract, and this is the fire locations of 4 megawatts, sprinkler controlled car park. Fresh air is coming through the ramp. Now, if you look at this here at 1800 seconds, which is 30 minutes, I have a temperature which is blue, which is almost like 49 degrees Celsius, because civil defense says less than 60 degrees acceptable. Visibility, I have the entire car park. So this is 1200 seconds, 20 minutes. So the entire car park having a 10-meter clear visibility, because my smoke extraction fans are running, and the smoke extraction fans are running and jet fans are running. Now, one more important thing is jet fan is working based on thrust. There is no flow rate taken as accountable because it's a thrust. It pushes the air from here, pushes here, pushes here. But this is the extract, right? So I'm still seeing they are designing this extract for 10 air change. It's a more conservative approach, but I would say this is a very high value. If you can do, try a CFD simulation with 6 air change only, even in the fire mode with all the scenario, you will be clearing the smoke in 1200 seconds. So when you have an engineered, what is the concept of engineered smoke control system is you need to engineer that. It is not pre-engineered. Pre-engineered is the one which you take from the shelf, apply it. But engineered smoke control system, they don't give you any parameters. You need to engineer a system. That engineered system shall satisfy the criteria. So here I could still see the many car parks are using 10 air change for 6 air change for normal condition and 10 air change for fire condition. Try a simulation with a 6 air change and see whether you can manage to get the criteria mentioned by civil defense. If you can manage the criteria, then why do I need to provide 10 air change, a huge fans, huge power supply, backup power supply? That's all for the presentation. Thank you. If you have any questions, please feel free to ask.
Thank you, Mohammad Basha. Hope it's very fantastic, very highly, deeply you explain about the car park ventilation, smoke management, and different way. So there is a couple of questions are there. So team members, if you have any further question, also put it in chat box. So as soon as possible, we can able to answer it. So there is the first question from, because the name is not there. The HRR is depending on the type of burning material or assumed area or burn.
The question is not very clear, but I will try to answer. The HRR is depending on the burning material. Okay. Remember, we are not considered that the entire building is in fire. Okay. That is called flashover condition. We will consider the burning material and later the sprinklers will be taking care. So HRR is clearly based, the Q value for the smoke management system, it should be taken based on the material burning. For to answer further, NFPA 92 gives you a formula to calculate how the adjacent materials will burn because of the original material being burned. There is a distance are given. So if you see, there are some potential materials can be burned because of this fire. Then you need to add the HRR of the potential burning equipments, anticipated potential burning equipments. HRR value should be added to the original HRR value if you have a very close distance. In the first example I have shown to you as an atrium simulation, I put 4 sofas purposely. I did not explain it actually. 4 sofas I have mentioned, and it is an automatic burning condition. Each is having 2.5 megawatt with a distance of 3 meter, but the other sofas did not get burned until 500 seconds. So it depends on the simulation, depends on the calculations, whether you need to consider the entire room or the particular burning material. But my assumption is to consider only the burning material.
Yeah, Mr. Bhaskar, you can just stop sharing the screen.
Yeah.
So I request all the members who's there in the online, if possible, who are possible, just switch on the camera. We'll take one group photo. Whichever possible people. Shall we go? Still anybody is going to open it? Okay. Thank you. Thank you. There is another question. I need a record. Yes, all the records and the details will be shared. The default history member, they will get an email. Non-history members also who are registered in the presentation, who are registered in the webinar, there is the email already sent by history team. So you can just reply back your email with your feedback with your full name. Who are looking for the e-certificate, give us your full name details within the capitals. So probably our team can communicate for the certification. So the same email, our team can respond back with your all presentation, whatever the calculation sheet which is shared by Mr. Basha. So it will be shared to you guys. There is another question I need to. Can we apply combined system natural and mechanical exhaust?
Okay, no, sorry for interrupting, Mr. Karthikeyan. I would just
Oh.
like to, I was just seeing the comment. There was one interesting question. So
Yeah,
I would
go
like
ahead,
to answer this first. By Mr. Mohammed Farid, of course, he's from Leminar, a CFD expert. Hi, Farid. Okay, but this is when we are assuming that the sprinkler will be activated only by the heat generated by fire. Okay, very good. That's Alpert's equation. What if the activation method is by beam detectors? Okay, question number 1. If you activate the smoke extract fan by the beam detector, how you size the smoke extract fan? The concept here I was explaining is the sizing of the smoke extract fan. You can activate the fan by any means, even manual pull station also you can activate. But what is the volumetric flow rate you will decide if you activate by beam detector? Because beam detector will activate the fan, but how to size the fan? To size the fan, you need to know what is the HRR is released by the fire. And the next is because for the large such as atrium with 20 meters height, we cannot rely on the sprinklers. Yes, we cannot rely on the sprinklers because by the time sprinklers area activated, the atrium will be full of smoke. So this is what I was showing you in the simulation also. You need to carry out multiple simulations to make sure what is the type of material burning, expected material burning, and when you are seeing, I mean, at what time you are seeing the smoke layer to descend down, corresponding HRR rate you can take for the sizing the fan. Also, what if the combustible available in the atrium is limited? Let's say only 3 megawatt are equivalent. Then maybe this equation will not give the right outcome for the higher height. Yes, it will not give the higher outcome for the higher rate. This is a very good question, and the answer is also you have given. The question is, what if the combustible available in the atrium is limited? Let's say only 3 megawatt equivalent. Then maybe this equation will not give the right outcome for the higher height. Yes, if you know a 3 megawatt, then you can size the fan for 3 megawatt. You do not need to consider this Alpert's equation. Okay, please, Mr. Karthikeyan, you were asking one more question, or we can answer it later. So the question you
my suggestion is we'll conclude all the questions. We'll answer to all the people.
Yeah, sure, we will.
Time getting late. That's it. We'll have a thank you note from our marketing head, Mr. Ajay. Mr. Ajay.
Yeah. Yeah, right. As we come to the end of today's interesting webinar, on behalf of FishRay Qatar chapter, I would like to extend our sincere gratitude to all those who made today's webinar a success. Especially our heartfelt thanks and gratitude to our distinguished speaker for today, Mr. Mohammed Basha. Thank you, sir, for all the enlightening, in-depth insights on today's topic. It was really helpful and value adding, especially the simulations and all the examples that you gave us. So we really look forward to have many more of such topic. Once again, thank you from our side. And special thanks to all those members attending today from different locations, some of you from the site, from office, for finding time from your busy schedules. Also, special note of appreciation to our organizing committee and all CWC members and technical support team and ISRE headquarters team. So that's it for today's webinar. Thank you all. We will be in touch with more such activities in the future. Thank you.
Thank you everyone for attending the webinar and the time you have taken to participate.
Thank you. Thank you once again, Mr. Basha. It's very humble and a good presentation. We'll keep in touch for the further presentations also.
Sure.
Whoever ISRE want to become the member, please keep in touch with us. So there is a next event, is a bigger event is coming on technical. That is purely only for the members. So you can get advantage on that. Thank you once again all. Good night.